Hello everyone, welcome to this session at reInvent 2020. Super thrilled to have all of you here. I am Neil Mitra, Principal Solutions Architect, had been with AWS for 4 years now, based out of New Jersey. I help customers like you in architecting IoT solutions using cloud native technologies. Very excited to have Shazan Bahrainwala joining me today from DENSO to share a glimpse of their innovation in the automotive space. Now you are here, I assume you are connected with the automotive industry in some way. Either you are part of an OEM, Tier 1, partner, mobility startup, or a builder passionate about automotive technologies. So by the end of this session, you will learn how you can accelerate building automotive-grade solutions using a connected vehicle framework that will help your organization to innovate faster and have an improved top line or bottom line. So what's in the menu? We will discuss what Amazon been cooking in the automotive space. Specifically, you will learn about a framework referred to as AWS Connected Mobility Solution and how it helps you to build automotive-grade solutions. Then you will hear from our guest Shazan how DENSO have extended this framework to build custom use cases that matters to their business. Finally, we'll show you a demo and provide actionable next steps. Please note, this is a 300 level session, so we will get technical. At Amazon, we are continuously listening to you, our customers, and evolving our ecosystem of connected services across e-commerce, streaming, personal assistance with Alexa, transportation and logistics, etc. And all this experience gave us insight into the entire automotive value chain and emerging use cases. As Andy Jassy says, there is no compression algorithm for experience. We had the opportunity to innovate on behalf of some of the most disruptive customers on the planet that you see here in their transformative journey. And while working with all these customers, we realized a set of common capabilities that every customer is trying to build on their own, related to fleet provisioning, fleet telematics, fleet management, which are referred to as mobility flywheel. This is better thought of a cycle, as your vehicle can continue to learn, evolve, be intelligent, share insights throughout its life cycle, just like our smartphones. And thus, we built a framework referred to as Connected Mobility Solution or CMS. I will use these terms interchangeably from here. CMS is open source, modular, customizable, incorporates different design patterns and best practices from the edge to the cloud. Our goal is to democratize the adoption of connected vehicle technologies for anyone. CMS has built-in capabilities mentioned in the mobility flywheel. It uses serverless technologies such as AWS IoT services for edge and ingestion, data lake services such as S3, Kinesis, application services such as Lambda. The platform APIs are built on top of these services to help customers like you with a foundation and accelerate your time to market with differentiating capabilities. For example, you might be building an usage-based insurance app which differentiates your business. So in the rest of the session, I will explain different design patterns using this technology stack that is used as building blocks for the CMS framework. But before we get started, there are two terms you should be familiar with. First is Electronic Control Unit or ECU, an embedded system in automotive electronics that controls electrical systems or subsystems in a vehicle. Examples, powertrain or brake control module. The second term is Telematic Control Unit or TCU. It's a type of ECU that deals with connectivity like GPS, Wi-Fi, 5G, etc. A connected vehicle will have a TCU that will collect data from different ECUs via CAN bus and publish to cloud to help generate insights. The other way to access CAN bus data is to use an aftermarket device, which I refer to as onboard unit or OBU. The device can connect to ODB2 port on the vehicle, collect CAN bus data, and publish to cloud. In either ways, you need to register the TCU or the OBU with a cloud endpoint, activate it, associate it to the end users. So the patterns I refer to from here are valid for both these kind of devices. So let's get started how it works. In the assembly line, the TCUs, which are embedded systems, are flashed with the IoT SDK, such as FreeRTOS, Greengrass, device SDKs. As the device wakes up for the first time, it will bootstrap, typically by providing a CSR or certificate signing request generated by the TPM or the secure element on the device. Registration can happen in two ways. Device can talk to an API gateway over HTTPS, invoke few Lambda functions to register the device, or through IoT Core over MQTT. You might be thinking, why do we need these Lambda functions, facade, provisioning? That is because there are different provisioning methods supported by IoT Core, such as just-in-time, bulk registration, fleet provisioning, and these microservices hosted on Lambda makes the framework customizable and reduces device-side changes. So as an outcome of this process, you have a thing registered with AWS IoT Core representing the TCU, the low privilege certificate that allows TLS mutual auth, an IoT policy that authorizes the TCU for different functions such as MQTT connect or publish. The asset library function allows the metadata information of the TCU to be stored in IoT device registry or in a graph database hosted in Neptune. So at this point, your TCU thing is created in the cloud. It has a serial number, IMEI, and it's tested in the assembly line to be working with a cloud endpoint. Now the fun begins. TCU needs to be installed on a vehicle. So it goes through the required system testing, quality testing, and activated. Additional vehicle information is captured, such as the different ECUs or domain controllers it's connected to, and can be stored in the asset library, as you can see in the picture. So if you already have existing data models such as this, you can leverage the templating capabilities of this framework and store the hierarchical structure in Neptune. IoT device registry doesn't support similar migrations today. At this stage, TCU is capable of publishing telemetry from the CAN bus using its SIM, but broadcasting of telemetry is still disabled. Now an user, let's say the vehicle owner, purchases the vehicle from a dealership, registers through an OEM mobile app. The workflow uses API gateway and Cognito for the owner to complete the pairing process with the vehicle, which in turn updates the asset library schema with the new owner vehicle association information. An activation process kicks off asynchronously to update the TCU status in device shadow. Device shadow is the virtual state of the device on the cloud within IoT Core. Upon the vehicle detecting the state change, it generates a new CSR to obtain a high privilege certificate from IoT Core. Once the vehicle gets this certificate, the old one is deactivated. At this stage, the TCU has obtained a high privilege certificate and is fully functional for telemetry and command control. The telemetry data can be processed through different workflows built within CMS. Telemetry data collected from CAN bus can be decoded or deserialized at the edge and published over MQTT, or published as it is and transformed on the cloud. We recommend MQTT since it's lightweight, supports pub/sub mechanism, but if your device only supports HTTP, remember IoT Core do support HTTPS and WebSockets. So now, the TCU is pushing telematics to the cloud. IoT Core uses rules engine to route different data types to different backend services. Raw data stored in S3, which is your data lake, your source of truth for analytics and long-term retention. Anomaly detection performed in near real time through random cut forest with Kinesis analytics. Telemetry data, DTC, drivers core are pushed to an Elasticsearch index for consumption through APIs or user interfaces. Now, the most hated word used by architects is probably, well, it depends. And that's because there are always trade-offs depending on the use case. For example, if you're processing millions of records and concerned about performance, use Kinesis for batching all kinds of data such as telemetry or DTCs prior to invoking Lambda. Lambda can transform the data within the stream. If you invoke Lambda directly, you need to monitor concurrency issues or latency with cold starts. If you're concerned about costs, consider using time to live options in DynamoDB, or clean your indexes periodically in Elasticsearch after taking snapshots, or use reserved instances for Lambda, Elasticsearch, DynamoDB, and other services. So the point I'm trying to make is customize the framework based on your specific needs. For event processing, the built-in workflow uses Lambda and SNS. So events from different sources, example DynamoDB streams, can generate alerts based on a subscriber's notification settings. Now, trade-offs. If you're concerned around performance or extensibility, use a robust event orchestration service such as IoT Events. No-code approach integrates with IoT Core, lets you build powerful state machine for processing millions of events. By now, you have provisioned your vehicles, which is cool, and collected fleet telematics, but how do you manage them at scale? For example, how do you find out all the vehicles requiring maintenance for a specific model in a geography? That's where this framework has a built-in web application that is hosted on S3 and rendered through CloudFront. The web application invokes APIs to fetch the data from Elasticsearch and enables different personas, such as Fleet Manager, with the entire fleet view. Data can be filtered based on location, anomaly detection, software version, etc. Cool thing is the APIs are also built with multi-tenancy in mind. So different personas can have different access control to the UI, which are managed through a Cognito user pool. Trade-offs? If you care about integrating your existing UI to this framework, just use the APIs and map your data models. If you need to bring your own identity and access management system, Cognito supports different mechanisms such as OAuth, SAML, etc. Or you can leverage the custom auth mechanism supported by different AWS services like AWS IoT Core. Visualization is cool, but as a fleet manager, you need to perform actions. Say all the vehicles with firmware V1 need to be upgraded to V2. So from this interface, you can filter the vehicles to perform over-the-air upgrade. Over-the-air upgrade uses IoT jobs under the hood. Firmware is pushed from a trusted source as a pre-signed URL concurrently to many vehicles. IoT jobs helps you with configuring deployment velocity, job aborts, retries, timeouts, notifications out of the box. Trade-offs again? If you plan to bring your own OTA solution, we offer all these APIs and microservices. Just test it out if your OTA solution is interoperable. Bringing all these patterns together, this is how the framework looks. At the bottom, you have all the core microservices which deals with the device lifecycle activities. We gave it a name, AWS Connected Device Framework, or CDF. And on top of that, we built the automotive facade layer with mobility-specific use cases. And together, they become Connected Mobility Solution, CMS. We have built a solution in a decoupled way to reuse the core microservices, aka CDF, for different industrial solutions beyond automotive. There is also an optional simulation engine, which is not in the picture, to help you quickly test out this solution with a virtual fleet. But we don't want to give you just a reference architecture. The entire solution will be available publicly very soon as a one-click CloudFormation template. How cool is that? Along with the source code to help you customize the solution. With that, please allow me to invite Shazan to share with you what DENSO is doing with CMS today. Shazan, the stage is all yours.
Thanks, Neil. Hi, my name is Shazan Bahrainwala, and I'm a senior manager at DENSO at our Seattle Innovation Lab. I'm here today to talk about how DENSO is building a new IoT connected vehicle platform that will allow the vehicle to run applications and process its own sensor and camera data on the edge. This will allow you as a developer to innovate with new product ideas and models and add new vehicle capabilities without requiring a large amount of cloud storage, connectivity, or remote processing. So let me talk to you today about the future of connected vehicles and make an analogy to the cell phone industry. When you got an upgrade from a regular cell phone to a smartphone, your world completely changed. You went from a cell phone that was simple and not very intelligent to a multi-function supercomputer in your pocket. Smartphones allow you to add new functionality via apps and give developers and consumers a full computing platform that unlocks new innovation. That's the change we want to make at DENSO with your vehicle. We are building the platform that will enable the vehicle to run applications as innovative as the applications that run on your phone. Our platform will unlock the data available on your vehicle to applications that can be installed on your vehicle. We'll give you the ability to process that data with a CPU and GPU, give you ability to run machine learning inference in a flexible mobile architecture. With this kind of platform capability, we want to unlock rapid innovation in the mobility industry. Before I start, let me give you a little background about DENSO and who we are. DENSO was established in 1949 in Japan. We are the second largest global automotive parts company in the world. Current products you may be familiar with include thermal, powertrain, mobility, electrification, and electronic systems. Last year, we had $47.6 billion in net sales, and globally, we're 170,000 people spread across 35 global regions. For the future, DENSO looks very closely at 4 core technologies to create new value and to influence the future of mobility. Areas such as electrification, automated driving, connected vehicles, and factory automation. It's through our work in connected vehicles that we've identified the need to allow edge computing in connected vehicles. So let me give you a few real-world examples of edge computing and what that means. We look at applications such as car security, usage-based insurance for insurance services, location-based services. For car security, we want to give the vehicle the ability to detect dangerous events inside and outside the vehicle using the vehicle camera systems. Let you proactively alert users before something happens and capture a video proof of security events occurring. This can all happen directly on the vehicle without having to upload camera data to the cloud. For insurance purposes, we want to give insurance providers the ability to base insurance risk on real-time driver behavior, location, usage, and vehicle telemetry. Edge computing gives them the platform to do that. This allows insurance companies to get to more precise risk measurement, also gives them ability to get better pricing for their customers. Location-based services like real-time mapping or ad targeting, logistics, and last-mile delivery services will gain the ability to actually run their applications directly on the vehicle, unlocking business innovation for them. So, edge computing with the DENSO Mobility IoT solution has a couple of advantages. Number one, speed and resiliency. It allows for applications that are very low latency and they don't require constant connectivity to the cloud. Edge computing applications are extremely cost-effective. They don't require transfer of large amounts of data to the cloud for storage or processing. These applications are privacy-focused. Private data never needs to leave the vehicle and be processed directly on the vehicle. Applications are updatable and can be modified over the life cycle of the vehicle. All this together will unlock business innovation. It'll allow developers and operators to grow new mobility business models. So let me talk about our product, Mobility IoT Core, and our Mobility Services Core, which is built with AWS CMS. The Mobility IoT Core is a hardware product and hardware reference design that can connect to the vehicle camera systems and the vehicle network called the vehicle CAN bus. We give you the ability to easily read vehicle data, vehicle camera data, and give you a flexible architecture to run your applications directly on the vehicle. We simplify the process of running applications and getting access to data for you. This in turn works with our backend called the Mobility Services Core. We've built this on AWS CMS. AWS CMS gives us out-of-the-box access to things like identity access management, platform APIs, application services, and data services. We then go ahead and add additional capabilities on top of that, including digital twin capabilities, mobility gateway, as well as anomaly detection, video on demand, and fleet management. All of this is based with a mobile architecture and flexible architecture. This allows us to build an automotive-grade mobility solution, which can be powered for our customers and lets them build a custom solution on top of that. Let me give you a few examples of what our hardware platform actually looks like right now. Like I mentioned, it's a hardware reference design. It's completely extensible. This platform is modifiable based on customer requirements. We're making it available first as an aftermarket OEM product, and we're working to integrate this into new and existing vehicle ECUs. The system will be able to connect to the vehicle camera systems and the vehicle CAN bus. We'll make available a CPU and GPU, give you the ability to run machine learning inference, and give you the ability to update your apps over time. So next, I'm going to show you a real-world example of an application we've built running on our platform, showing how we can use edge computing to actually detect security camera events and combine that with the power of the CMS system. In the demo, I'm going to show you a very common scenario. You have a vehicle parked in a parking lot, and somebody's backing up, and they're now going to cause a collision with your vehicle. This happens all the time. In this scenario, a collision occurs, the person driving the offending vehicle gets out to go check what happened. They see they've caused some damage, decide they don't want to deal with this. They get back in their vehicle and drive away, causing a hit and run. Today's world, this happens all the time. You're out of luck most of the time. With the Mobility IoT Core platform, a security camera application can continuously record camera and watch the camera. It can detect when a vehicle is backing up and about to cause a collision. It can detect when a collision occurs. It now captures this event data, packages up information about the event, including a video clip about the event, and automatically uploads this to the cloud. This is all happening on the edge, and only when an event occurs does it actually transfer data off the vehicle. So now I'll show you what this looks like on our backend. We see the event occurring, we see when it occurred, where it occurred, and what the cause of the event was. We then also show you a video clip of the event actually occurring. So now here is a short little clip. The vehicle is backing up, the vehicle will cause a collision, and then we now have proof of all this happening. Our architecture is completely event-driven. So from here, we can take it actually one step further and complete the scenario. When an event occurs, the system can actually activate a live video stream from the vehicle. This happens on demand only when needed, so we're not streaming continuously. When you activate a live video stream, we can now actually see that the event has occurred. We can see somebody getting out of the vehicle, seeing that they are seeing the damage and not doing anything about it, getting back into their vehicle and driving away. So this is a real-world example of how we can use edge computing to detect the event, capture relevant data about the event actually occurring, and add additional capabilities on top of that to see additional capabilities. So I'd like to talk about how we actually built an application like this using our platform. So we have a Mobility IoT Core device in the vehicle right now, and this is again capable of reading the vehicle camera systems. We take that vehicle camera stream and break it up into 3 distinct video streams to allow us to do multiple services directly on top of that. We take one video stream that we've broken up using GStreamer and make that available to a security camera application running on the platform. This application is capable of taking a video stream and combining that data with vehicle telemetry coming from the vehicle CAN bus. This application will detect meaningful event data when a collision is about to occur or when a collision has occurred, and then take this event data and send it over MQTT to an IoT rule in our Mobility Services core. This IoT rule will then write this event data to an event database. Since it's all event-driven, the same application can take that event and cause an alert on the vehicle to actually have the vehicle honk its horn as detecting a preemptive collision. You can try and stop the collision even occurring. You'll also send an event now to a video clip capture service. Another video stream is continuously capturing video clips when requested. It'll capture a video clip when requested and upload that video clip straight into an S3 video bucket storage. We then use an API gateway to combine S3 video storage with event data and make that all available in our user interface. So to complete the scenario, we also want to be able to enable a live stream when an event actually occurs. So the first thing we do here now is we activate Kinesis Video and create a WebRTC signaling channel in our backend. Next, we use IoT Shadow to send information about the signaling channel back down to our devices. And we also use that same signaling channel to activate the WebRTC SDK on our device. It's really important for us to not continuously stream data if it's not requested. So we activate WebRTC SDK, we get signaling channel information, and then the user interface will use that signaling channel to negotiate a video stream and make a peer-to-peer connection and enable a live video stream from the vehicle. So here's a full example of how we're able to take a video stream from the vehicle, break it up into detections, capture video clip information, and also enable live streaming. All the processing and data collection is happening on the vehicle, not in the cloud, and only meaningful event data is being uploaded to the cloud. So with that, I'd like to talk a little bit about lessons learned as we went through this process. Utilizing the CMS reference architecture significantly accelerated our development time. We got to speed the first prototype very quickly. Using AWS tools allowed for easy trial and experimentation. Our developers learned by building. And most importantly, a close collaboration with AWS allowed for quick problem solving and helped build new solutions for us very, very quickly. And with that, I'd like to hand it back to Neil.
Thank you, Shazan. Very insightful. So you learned a lot in last 30 minutes. Let's summarize. We started with what Amazon been cooking for the auto industry and how we learned about mobility flywheel, a set of common capabilities in the life cycle of a vehicle related to fleet provisioning, fleet telematics, and fleet management, and how CMS can support those out of the box. CMS is pay-as-you-go, open source, modular, customizable, going to be available as a one-click deployment to CloudFormation. And then you heard from Shazan how DENSO accelerated their time to market using CMS as a foundation. And on top of that, they built advanced video use cases to deliver an automotive-grade solution that matters to their customers. There is one more thing. I'm very happy to share with you. We are bringing live video capabilities to CMS in 2021. Stay tuned. If you're hungry to learn more about other automotive journeys on AWS, check out these sessions from BMW, Toyota, Accenture. With that, I greatly appreciate you joining us today. Remember, the journey of 1,000 miles begins with a single step. And we are here to help you take that step, to help you reinvent the future of connected vehicles. Thank you.